break first break you can take you don't want
Okay, welcome to day 3 of the JAM course on Chain of Things, a course on blockchains and IoT. So today we'll explore scalability issues in blockchains. So we did have a bit of a background on scalability yesterday when we talked about consensus, and we discussed a bit on what it means to have a fast consensus. And today we would see what are the other ways in which we can scale blockchains and why we need to do so. So brief recap, yesterday we talked about two things. One on consensus. The first session was on consensus, and then transactions. And we also looked into Professor Pal talked about some of the applications of blockchains for IoT. So today we will see why blockchain scalability is a big issue in blockchains and some of the scaling solutions that we have. Why are these important? The most important thing is because for IoT applications, you have a lot of data to be stored on the blockchain. If you want to store data on the blockchain, then it's a lot of data. We don't generally store data on the blockchain. But think about a sensor sensing something, and it is sensing at regular intervals, say maybe every second. And think about the amount of data that is being generated by the sensor. It's a lot of data, right? And if we try to keep it on the blockchain, then it's going to be extremely large.
storage.
Exactly. Storage would be a big problem. So, all sorts of applications have these scalability issues. We will first see today that how blockchains today, the blockchains that we have today are suffering from scalability issues. And tomorrow, when we talk about IoT applications, tomorrow and the after would be more on the application side of things. We will see why we should not store all this data on the blockchain and what are the other ways of doing it. So scaling, why scale? It's very simple reason is that if you look into normal currencies, you will see that Visa, PayPal, they can scale quite well. However, for Bitcoin, Ethereum, it's pretty less, I would say, where Visa can do 2,000, 2,500 transactions. Bitcoin does only 7 and Ethereum does only 20. It's like a little bit old data, but I would say like this is what happens. And then we also see that the average cost of Ethereum transaction in USD is also pretty high. So this is again a little bit old data, but this has really this has reduced after the merge. We talked about merge yesterday, right? Merge is when the community moved from the proof of work to proof of stake based model. So why is this so slow, and can we speed it up? So this is a question. Why are these transactions so slow, and how do we speed it up? Any guess why these transactions are slow?
There's too much process behind the blockchain.
Too many
processes behind the blockchain.
What are these processes?
Gathering of resources.
Yeah. What are these? Broadcasting, verification.
Solving a puzzle.
Yes, exactly. So the consensus broadcasting in this big network. then consensus, mining, those are the things that slow the system down. And that's why, yes, yesterday we were talking about this Bitcoin, and it's taking almost 1 hour to have full confirmation, and that makes things really very, very slow. So going back to where we started, and I said, I'll show this picture every day, and literally I meant it. So you did see that the first step is create transactions. Then, your transactions are put in a block. And we talked about yesterday, if you remember, I keep saying these older things so that, it just shows to help you see the connection of the different topics that we are learning. Yesterday, I also told you that these transactions, these are selected by, either we call it validators or miners, who has essentially put transactions in a block. And then it is, some transactions might get into the block, some might not. There are all sorts of challenges, but let us assume for today that you have a set of transactions to be transactions that are put in the block. We'll come to this topic actually, where transactions can be really censored. Censorship means I'm just including the transactions in the block. Okay, it's a very big challenge in blockchain. And making censorship resistant blockchains is a very active area of research in the community. Now, so, these blocks are, the transactions are put together in a block. The blocks are broadcasted in the network, and then you have the blocks being verified by this, by the peer nodes. And then, only then, these blocks can be added on the blockchain. And we saw yesterday this adding of blockchain, and when you add blocks in the blockchain, there could be forks. We want to get rid of forks. We want fast finality, meaning that when we showed the Bitcoin, you need to wait for 6 blocks for complete confirmation. We need fast finality. What does it mean to finality? My transaction is finalized, and we want it to be as quick as possible, right? Because you think about it, if it takes you 1 day to settle a bank transaction, would you like it? No, right? And this was a very big problem in the case of remittance. So let me just give you this, since we are talking about this, I'll give you some good examples where, why it is important to have fast transactions, efficient transactions. So think of remittance. In earlier days, what used to happen is that if you have like doing this currency exchange and sending money over, it would take a long time to receive that money. And this was because there were lots of these, that there has to be lots of checks and balances to be really complied upon. And especially, I have seen quite a few reports, especially if you are, trying to transfer to many countries where there are a lot of these, there are bulk of transactions going, bulk of remittance transaction going, things can be extremely slow. And in those countries, I know in Africa, there were quite a few blockchain projects which were run very successfully, where they used it for remittance. It was very, very successful. They were able to reduce the time from few days to few hours, which was really good. Because think about it, that, someone in a very remote part of the world who needs money, if you can't send him at the right time, then it can be extremely, difficult situation for them. Actually, I'll just pause here, because blockchain, if you think very clear, think a bit, there's a lot of good use you can put this blockchain into for having, some kind of to achieve more social good, because, it's a democratic way of dealing with things. So it's there are many countries who have embraced this technology quite a bit. Yeah. So it's slow. Again, we talked about it. So this is because as the consensus is slow. Your broad blocks are being broadcasted and so on. So this brings to this question of this scaling trilemma. What does it say? So it says that scalability, decentralization, and security is very hard to achieve at the same time. So think about the system, the blockchain system. You have security, you have this immutability, it's very secure. Because the cryptography underneath is very secure, and the way the cryptography is used is also very nice. So the security, it has, if you try to have decentralization, the more the number of nodes, it is hard to get it, hard for scaling it efficiently, right? So there's always this question of how do I balance the three things, and it has been shown that the scaling trilemma essentially says it's hard to achieve scalability, security, and decentralization all at the same time. So we have to compromise one for the other, and because of this reason, people have been trying to find a nice balance between the three things, because all these are requirements. I need decentralization, at the same time I need to scale, I need good performance. So I need more nodes, and I need them to be perform the blockchain to perform well. I need high security, but all cannot come at the same time. So how do we balance all the three things together? And what we call a good balance? Good balance is when the application that we are using it for has all the properties that we need, or all the good things that we need from that application. So scaling, one of the big scaling ways of scaling is to design better consensus algorithms. So yesterday you saw how we looked into first Bitcoin, and then we looked into Ethereum. Bitcoin is like much slower than Ethereum, and the proof of stake as such, proof of stake protocols are extremely fast compared to the proof of work. And the proof of work is slow because you are doing a lot of computation. You're doing a lot of hash computation, as we saw yesterday, right? Tera hashes per second, millions of tera hashes per second. And the main purpose of doing this proof of work is to do some computation, right? And you don't want to be able to you are spending all that resources in order to do it. So proof of work has been really slow, and then proof of stake, as we saw, it was quite fast because of the things that we are trying to do are simple. We are choosing a leader. So yeah, the leader election mechanism, when the block proposer is chosen, that has to be fast generally. I mean, that has to be fast for the whole algorithm to really give you good results. But then, it was much easier because you had the committee. The committee was making a decision. It was a smaller committee. It was not everyone. So it was really nice. And we had this randomness as well, which made it hard for people to guess what is coming next so that they can attack. If you know what is happening next, then it is very easy to launch an attack, right? So just a good thing. You want to you want to attack a person on the road. You want to rob a person on the road. If you knew that this person would come, you would actually have a better strategy, wait to mark that person. But if you have no clue and you're waiting for a particular person, it's coming at random times, and you have to wait for a whole day to get that person, right? So it's very simple. I mean, it's a very easy example to understand that it's the randomness, when you cannot predict something in advance, it's very easy, it's very hard to attack. So all these blockchains, for example, Algorand, Cardano, Ethereum. I should not have said Ethereum 2.0. 2.0 is gone. It's now Ethereum. It's now Ethereum, and the 2.0 was an intermediate step when they were transitioning to the proof of stake. So this is a mistake. Please note it down. So and then we had so we talked about, we saw that we briefly mentioned about Solana, which is also very fast, which have extremely fast, and the Red Belly blockchain is a product from Australia. So we the main proponent of this Red Belly blockchain, they the proposal of this Red Belly blockchain is very also very interesting, and it's also a very fast blockchain. Algorand, it's like a little bit of history there. Algorand has been a remarkable blockchain. I don't have time to discuss Algorand. Each of these algorithms are extremely very good. So I would recommend all of you to go through and read the techniques, why they are fast and how they work. So in a course like this, it's very hard to talk about everything, but for all those who are interested, it's good to read about how they were built. So there are very, I mean, the Algorand and these on the websites of each of these, there are a lot of the first paper, or the most important paper, and then there are a lot of the variants for for each of these things. For example, Cardano, there's a list of nice works that essentially explain different features. And the Algorand there's a nice paper you can definitely read. It's a very good one. There are a lot of videos online. So for those of you here, I would say that this topic over here is like there are very well made videos that you can see on each of these things, explaining each of these blockchains in greater details, and why every step is explained. Why are they doing it? It's not like a random choice, like I do this. So they are not only well explained. If you look into the papers, you will see detailed proofs as to why it works. So, those who are really curious, this is a time when you could essentially go back and read more about these things. Now, with the proof of stake or any consensus algorithm, the only problem is that it can scale to a certain extent. Okay, so for example, today, I talked about Ethereum. Ethereum is a very nice example. They had a proof of work protocol, right? And then they migrated to proof of stake. It was not a very easy thing to have that hard fork and be able to move. They had to they had years of working on the other chain, trying to perfect it before they could go into the merge. Now think about it. You have already a blockchain running and you want to improve the scalability by improving the consensus algorithm. Improving the consensus algorithm essentially means that you have to do away with your, you have to have a new client altogether, right? And everything is new. So the way your block generation works, the way your consensus works, that's part of the consensus, but the block generation, how it is distributed, who essentially verifies, all these steps have to be tailored according to your new algorithm, which essentially means all your code has to be changed, right? So, and everything has to be updated. And when you're doing an update, so when you think of this blockchain, it is not like my, assignments that, I'm doing to get the marks or, just show it. It's also, or, just to understand, when you're building real software, there has to be a lot of tests and to see if anything is going wrong, because you are deploying this product in the market. It's not like, it's a toy, right? So there's a lot of stake involved. So there is, for this reason, when you have a new consensus algorithm being, already integrating it with the existing system, there's a lot of things to consider. And that's why when you're scaling, you're designing a new consensus algorithm for an existing blockchain. It's very hard to integrate it, and it takes a lot of testing and so on. And the other thing is that this it's kind of a limit. I mean, I would say some kind of limit to which you can design better and better protocols, right? So compatibility with the existing blockchain is one of the main issues. And then you are designing good protocols. There's a lot of these consensus algorithms, as I showed you the last page where you could see a number of consensus algorithms. So they can scale only to a certain extent, right? Beyond what goes beyond that. So let's see what goes beyond. What are the other ways we can do apart from designing consensus algorithms? Questions? You are quiet today.
What is a Bitcoin Cash?
It's a fork from the Bitcoin.
Similar to Bitcoin?
Yeah. Questions? Mm-hmm. Okay. So we talk about something else. So these are called layer 2. And let me show you the layers, because layer 2 might mean, you might be wondering what is layer 2. So look into this picture on the left. It's not very clear. Can you see the back? Yeah, okay. So you have this hardware layer, you have the network layer. Hardware is your real device. Then the network layer, you are using you're using this peer-to-peer network to distribute your blocks and your transactions. And then you have the consensus mechanism sitting on the top, where this is a logical thing. Like think of the layers as logical layers. Okay, not you cannot possibly logical layers. So this is network layer where you are broadcasting your thing, and then the consensus mechanisms which are essentially running. So till this point is what we have in the normal blockchain or the layer 1 blockchain. So Ethereum, Bitcoin, whatever, Cardano, Solana, etc. They would all have this kind of a thing, right? This part, which is like, they would have similar things. Now, what this layer 2 does is that it builds over the actual layer 1. So it builds on the actual blockchain. What does it do? Very naively, you see, whenever a transaction takes place, what do? We write it on the blockchain. Then we verify if the transactions are correct. What layer 2 does is that it considers off-chain transactions. That means that not all the transactions are written on the blockchain. That is what we call an off-chain transaction. Now, what this means is something of the sort that if you say you are sending a rent every month, right? What you could possibly do every time you are sending the rent, you are writing this information on the chain. Okay, and every time you're writing, it means that you are executing a transaction. That transaction has to be verified. It's a long process. Instead, what you could do is that you can pay the rent directly off chain. What are the problems? You don't write it on the chain. Huh? Okay. Let's talk about the problem first. So I'm Alice. You are Bob. I'm paying the rent to you every month or every week. So every time I pay you, I'm writing it on the chain. It's a transaction, right? It's a transaction from me to you, and it's written on the chain, right? Every time I write this transaction, I have to verify this transaction, right? It's a long process. It goes into the long process. Instead, what we do, I send you pay you the rent, and it goes on for, say, every time. It's not never is it written on the blockchain. So I write it I write it only at the end of the year. Okay, this is the amount of rent I've paid. What is the problem with this approach?
They were missing transaction history.
There will be missing transaction history.
Immutability is
proof.
lost.
Pardon?
Immutability is lost.
There is no proof.
Immutability. How is immutability lost?
Someone can alter the transaction to say you have not.
Yeah. There's no proof, exactly. There's no proof. So what I could do is that I might, not pay the rent once, and then how is he going to prove? At the end of the year, I will say, no, I've paid everything, right? There's no way for, you need, every time I'm paying, he gives me a receipt. It gets into, not gives me just a receipt. It is written on the chain. Yeah. If I miss something, then and there he can say, no, you have not paid the rent, so the contract is cancelled, something of the sort, right? So I can take decisions very quickly. You need, else what happens is that at the end of the year, there's no mechanism to prove who is right, or he is telling he's not telling the truth, or I'm not telling the truth. It's like very hard for everyone to understand. So, but there are mechanisms that will help us to resolve this thing, even if these things are off chain. If we could do this, instead of writing every transaction, every rent transaction on chain, I write it once at the end of the year. And if I can show that all the problems that you talked about, no proof, immutability, etc., then that's a good idea, right? If I'm paying for 52 weeks, I'm saving actually the cost of 52 transactions, possibly. Maybe, you don't take 1 or 3 transactions. So if I could do that, I could do off-chain transaction and still be able to get that security guarantee. That's what I want, right? Does it make sense? Not. Okay. So off-chain means I'm not writing everything on the chain. That is off-chain. When you're writing, it is on-chain. When I'm not writing on the chain, I'm not involving the chain, I'm blockchain, it's on-chain.
What is the
Okay.
layer 2 role in?
Huh?
What is the role of layer 2 here?
I'll talk.
Okay.
Ma'am, is this secure, ma'am? Off-chain process.
Yeah, off-chain process. We have to make it secure. So that's a requirement, right? If you do off-chain, you have to make it secure. So that's a requirement. Okay. So I give all these examples so that it's easier for you to relate to the problem from a practical perspective. So if I take this approach off-chain, I'm not going to write everything. I'm saving the cost of, I'm making it faster because I don't have to verify many things. I could possibly scale, but at the cost of security perhaps. But if I can design protocols where I can do off-chain transactions, having the same security guarantees, that's what I want. That's my goal, that I would do off-chain transaction, but have the same security as my normal blockchain. So that's what I want. Okay, I'll pause here. I want you to think about it maybe for a few seconds and ask questions if any.
Is it worth going to off-chain? Again, we are talking about security. We're losing our security.
No, that's what I'm saying. If we do it a naive way, we are losing security.
Yeah.
But if we do it in a clever way, which we will show how to cleverly do it, then we will gain. So I've not talked how yet. But why I would like to do off-chain? Is that clear? Why? Is the why clear?
To save resource.
Yeah, you are saving the cost of multiple verification. Why is clear to everyone?
Why I want to use this layer 2 solution, ma'am?
I
So-
don't know.
Why off-chain? Do you understand why off-chain? Huh? Now I've not talked layer 2. Layer 2 is off-chain, actually. Layer 2 is off-chain. I'll talk more about this, the term layer 2. Off-chain, why we are doing off-chain? Is that clear?
No.
Okay. Now I have not said how. That's the question, right? That's the question. And you can solve it in many ways. What are you doing? So why is clear. What you want is that I want to reduce the rights on the blockchain. At the same time, have the same security guarantee. That's my what. So for everything, you have a why, what, how, right? Why is the most important thing before you start a project? Why am I doing this project? What do I want to achieve? How will I do it? Right? We're breaking it down. Now, problem is clear. Why off-chain? What do I want to achieve? Is it clear? Now, the only question remains, I think is the most difficult part, how? Even why? I think whoever said for the first time that we can do off-chain, I think that was something very interesting. I think why is very important to ask. So for anything, like why should I be doing this in the first place? Anyways, so this is what we want to do, the off-chain transactions, and this is called the layer 2. So essentially, all off-chain transactions would be my layer 2 transactions. Whatever is happening off the chain, it's not being written. It's between you and me. That is off-chain. Blockchain is not involved. That's off-chain. That's what we are also calling layer 2. And this essentially is expected to improve my transactions per second. And the most important thing is that even while doing off-chain, I need the same security guarantee as I would have just with the layer 1. So the layer 2 should provide the same security guarantee as layer 1. Now, we will see that some layer 2 solutions, and we will see like when you will get the same security as a layer 1, when you will not get the same thing. And these are things that we were going to discuss. Yeah, honestly, these concepts, if you're hearing for the first time, it's a bit hard to grasp. But I mean, if you listen to these things again and again, these things will come about. Yeah. So maybe I'll just give you a word of inspiration. When I started doing blockchain, I was not so young as you guys, many of you guys. I had a lot of maturity. When I'm saying young, it means like subject-wise maturity. But honestly, I had struggled. I really struggled with the Bitcoin understanding, because there was nothing at that time. Ethereum was just coming. There was not enough documents and documentation. The Bitcoin was the first thing that I started. I did not understand it was like extremely hard for me to really make it understand what was happening in the first place. This model itself was not very the normal models that we see in computing, right? It is actually in some way if you stitch the pieces up. But there were at that point of time so few resources. Everyone in the community who had started at the time were really struggling. And the best way we found was good way to go forward is really understand small bits of it, look into the piece of code that is available, try to see how to do a transaction. I still remember I was sitting in a class with my students. It was a security course. I had decided to teach blockchain. After the class, we were struggling to understand a particular thing. And one of my students started with, mining some Bitcoin by doing some surveys and all, just to see how things are. So if you really want to understand this, any topic, that sort of thing, you have to really get a feel of it by doing things. So there are a lot of resources now, and you're very lucky. You are at a time when you have a lot of resources. But throughout your life, you would see, especially in technology, you would see technologies coming up for the first time when there would be nothing. Or maybe you are proposing something, you are building something. There would be not much resources. So you have to have that thing to be able to understand, okay, fine, how do I go forward understanding these things? So, it's hard for you at the moment because you are hearing it for the first time. But, if you get interested, I'm pretty sure, if you go through some of the literature, you'll get a better grasp of this topic. And there's lots now on the internet. So what are some of the solutions of having of this layer 2 channels, payment channels and state channels? These are, oh, the Raven is gone, so it's a bit of an old slide. Okay, so the Raven network is gone. Lightning network. So what happens in the payment channel is that these are for payment. What is happening here is that I do off-chain transactions, and I'll show this in a bit. And a generalization of the payment is called the state channel. We will not talk about it here much, but we do have an expert here sitting here in the room, Shruti, who is actually doing a PhD in payment channel network. So even after this class, you can talk to her. You can discuss with her. You can discuss with me as well after the class. But I'll not go much into the payment channel and the state channel networks. But these are very interesting topics to explore. Side chains. I talk about side chains, plasma, and mostly the roll-up space. So the idea of all of these is that your main chain is somewhere you write fewer transactions, and most of the transactions you are doing in some other chain. Okay, and depending upon how you do it is what makes it distinct from one another. Now, let us look into some of these things in a little bit more details to understand how each of these solutions work. Okay, so naively, this is a very, very naive way of doing things. I'll give you a very high level without going much into the details. So think of off-chain payments, and this is one example where I was talking. You are paying the rent many times, and you are making n times you're paying the rent, n transactions, and n writes to the blockchain, right? Now, what you would do is instead of the payment sending the payment every time, you are going to do only 2 transactions. Instead of n transactions, you would do 2 transactions. How would you do it? The first thing that you would be doing is you are opening a channel and you are depositing some money. And you, at the end, after all the transactions have taken place, you are closing the channel. Those are the 2 transactions that you would be doing or writing on the blockchain. So instead of n transactions, you would be doing only 2 transactions. But the crux of it is that how do I ensure that having this channel, having this transaction done in this way would guarantee the security as if it was a normal Bitcoin, comparable to the normal Bitcoin security. So the way this is done at a very high level is that the money is essentially locked. So there's you can actually lock at the time of opening the channel, and you can lock a value. Say you have locked $10. So the maximum that you can send from Alice to Bob would be $10 and not more. So amount would be fixed by the size of the capacity of the channel. And then there is a mechanism which says that if something goes wrong, then you break or you abort and you write it on chain. So for example, there is some kind of a if something goes wrong at this time and Alice does not pay or something, or anyone can, if they don't follow the protocol, then you can abort and abort the channel, close the channel, and because you had locked in that money, you can really retrieve it. So either you abort completely or and get back the money because that was locked from before. So this is the overall idea of this payment, of the off-chain payment. But there are a lot of these, very finer points over here that I will not talk about. I will not talk about. But if you are interested, we can have a chat after the class during this, during this time to really understand how payment channels work. So I decided not to discuss payment channels because these payment channels are essentially for payment networks, and I want to use the other techniques to when I explain some IoT applications. That's the only reason I'm not talking about this payment channels, but it is a very interesting interesting direction. One of my PhD students worked a lot on this space. So I'll talk about this payment network because Alice and Bob might not have payment channels, be able to have these payment channels because they might not be in a position to deposit the money between Alice and Bob. So they can essentially have intermediaries with whom they have channels. So instead of sending the Alice and Bob anything, you would have a channel with Alice to Eve to Dave, and then Dave to Bob. So you can have 3 channels like this. So instead of one channel between Alice and Bob, you could have other channels. You can have a path to Bob, and then between these channels, you will be opening the channels and closing the channels and making payments off chain. And this would happen for every channel to be able to send the money from Alice to Bob. So at this point, I'm just keeping it just like this, saying that there's very well developed literature in this type of work, and anyone interested, there's a lot of interesting problems also could look into details, or I would be happy to discuss more. So Shubhra is again my PhD student who worked very deeply in this whose PhD thesis is on this problem. Okay. So the main challenge with channels is that if I want to create a channel with you, okay, if I am paying you a rent, I have to create a channel with you. You have something like, you might, because it's in your own interest to get that money, so you might be interested. But it is possible at the time of creating the channel, both the parties have to lock some money, and you might not be interested, right? Because you also lock money, because if you are misbehaving, then your money is slashed. So that is why it's a both way. It's a depositing the money is both ways. So you might say that, look, I mean, I'm not going to give any deposit, right? I don't have to. I'm an honest person. I really don't want to deal with you. I don't want to participate in opening a channel. So sometimes it might happen so that it could be hard, and then you have to find other participants and follow a path to reach Bob. And one of the other things is that this path has to be known well in advance. Now think about it, that it is a very big network, and one of the parties has, who had locked up some money, his money is locked, right? You cannot use that money for that duration of the time till the channel closes. Any locked up money, some people might say, no, it's locked up, I need this money. So it's not a very good option. So all these concepts, when you think, it comes from real life, right? That's what people would want. Like some people say, okay, fine, this is locked up because I can use this for some time. Some people might say, no, I mean, I don't want locking things up at the end of the year. I will not want that. I would rather have that fluid money so that I can do other things. So this is one problem with this blocking up funds, because there could be long blocking periods. And again, it's very application specific. It just deals with the payments. So this is not a very good option for many applications such as blockchain. IoTs. Oh, okay. Pause. Questions? Yeah.
How does the validation work in this process?
Okay. So the validation is a normal normal transaction validation. So the last transaction that is written, that is a normal Bitcoin validation. But as I said, that you could go wrong. If you have, if you are cheating, then you can abort, right? So you are writing a transaction back. And when you're writing the transaction back on the blockchain, there's something that there's a mechanism to help you prove that there is a misbehavior. At the time of misbehavior, to prove that there is a misbehavior, only then you can write back, and from there the validation is a normal validation. But what I did not tell you is that how do I prove this misbehavior? Yeah.
Between two parties, who's going to write on chain the transaction details?
Okay, so the transaction details are actually, when you are opening the channel, that is a channel write. Both the parties are involved.
Closing the channel?
Closing the channel also. But as I said, if you're aborting it, then the channel is closed, then it is something that one of the parties could initiate.
How will you know, like, who is going to, like...
Yeah, that's what I'm saying. That is what I'm not talking about. How would I prove that, yeah, exactly. Any more questions? Okay. So let's then talk about another thing, which is called a side chain. Now, side chains are also quite an interesting concept. So what happens is that this black one is a main chain, and mostly all transactions happen. But there could be side chains that operate independently. So I could have my own side chain with my own way of consensus and so on, and I could actually communicate with the main chain in some way, and all the transactions that are happening could be on my side chain. I'm not a part of the main chain. I'm not a part of Ethereum, Bitcoin, or the underlying thing. I am on the side chain. I have my own side chain project. I have my own set of nodes. I'm doing all these things on the side, where you can have a lot of these transactions. So here, this is my on chain. This is my off chain. It looks like a chain. It's another chain, but this is not the normal, the layer one. This is another chain, but that's something else. That's a different project. Okay. So for the side chains, is that there are independent blockchains, and they are somehow compatible with the main chain. The side chains have their own consensus mechanism and the block parameters and everything. And once transactions are confirmed on the side chain, these are written on the main chain. So everything happens on the side chain. At the start, there are ways to actually ensure interoperability. So this is an important concept, because this is also something that I will briefly touch upon later. So these are different chains. All transactions are happening here, and there is a mechanism to write back on the main chain. Interoperability is made possible using a two-way peg bridge. So bridge is another, it would be another client that would take inputs from from this and the DApp chain, just to connect both the two, so both the chains, and then the contracts that are deployed to the main chain can be directly deployed on the side chain. And main issue with that, the security of the transactions would depend upon the security of the side chain. It does not depend upon the security of the main chain. If the side chain has gone corrupt, side chain is have spurious transactions, then it's gone. I mean, it's not going to be it's going to be incorrect. So here, in this case, in the case of side chains, the security of main chain is not guaranteed. So if you are relying on side chains, if you are doing things on side chain, you might have faster transaction processing and finalization, but you would not get the same security, because the security, it's something like you're just writing things out. but you are not checking on the chain, on the main chain. So this is your main chain. You're not checking here. And that is why the secure, it's not going to be, it might not be secure. Make sense? Makes sense. It is something like you're taking the head of a third party. Now the third party is doing everything, it's processing, it's validating and everything. And you're simply saying, okay, I've done this transaction here. That's it. So if that third party is not behaving properly, then your transactions might not be correct. Performed. Okay, security of the system relies on the security of the sidechain. Yes, questions?
Isn't that the same same for the channels as well? Like
No.
the security of the system relies on.
Because the opening and closing of the channels are the main things, and those are done on the chain. Anything that is happening. So here, if something goes wrong here, I have no way of proving to the main chain because the main chain is not bothered.
Okay.
Because when I say I'm operating on the side chain, even I might not know that it is essentially being, that it would be something that would say like it's connected, but there's no dispute resolution strategy here that is resolved on the main chain.
So, ma'am, when we start with Go Ethereum, normally we connect to the Ethereum and we start our private blockchain. So, those are also side chains.
No, that's not a side chain because that is essentially, no, that's not a side chain. That is Ethereum. So as I said, it is linked with Ethereum.
Yes.
Right?
Yes.
So it is the same chain. It's just being visualized in a different way.
But in that also we provide one admin. It's
Yeah.
like it's the Genesis block starting, and after that we connect multiple systems to that. So this is the kind of bridge my system will work, because if I am connecting this system to the Ethereum, I'm just connecting it to the chain, and then after this will be my admin.
Yeah. So what I'm trying to say is that if you are doing things on a test net, right? So testnet is separate, right?
No, ma'am, I'm talking about the main Ethereum that we are getting connected with Go language. And, we are starting a different chain other than Ethereum. So here when we start, it shows us the 0 peers, and when we connect multiple our system in a private network, then it will work like.
But where is this validation done? Is your transaction written on the chain?
No, transactions will happen in my private chains only.
Yeah.
And then how to write it on Ethereum means I'm not clear about this concept.
Okay, so there are two things. When I say on chain, the validation should be done on chain.
Okay.
So if your transaction validation is happening somewhere else, that's not what we are talking on chain. But what you are talking about, essentially everything goes on being validated on the chain, right?
Yeah, right.
So that is a part of it.
Okay,
That is a part of the main chain. That's not a side chain.
So what's the project actually working with sidechain?
Side chain is, for example, DAI is a side chain, Liquid is a side chain.
Polygon.
Polygon is like a very
Polygon,
big, Binance, these are all side chains. Yeah.
Can we create our sidechain practically?
Yeah, practically you can also create, but whether people will join it or not, that's the difference.
No, that's okay. But how could we start? Means how can I start my sidechain with the main Ethereum chain?
So yes, so that is how you would connect with using some bridge.
Bridges like?
Bridge is like another software.
Okay.
Yeah.
So software with the.
Yeah. Now bridge also, if you think of bridge, there are also well-known bridges, which are there are bridges which provide that service of connecting the side chains with the main chain.
Okay, that might be another project.
Yes.
With which I can take help with. And ma'am, what is the difference between sidechain and parallel chains?
Parallel chains. It is, I mean, if I understand correctly, what is an example of a parallel chain?
Like again, the one chain is just like running here. So these are the side chains that you are connecting with it. Parallel chains are still the same thing like running with chain.
Okay. I'm not too sure about parallel chains, so I'll not give you an answer to that. I have to see. Okay, but I think for what you say, parallel chain, I think it's parallel chain is also a type of side chain, or it's a different nomenclature. But I don't want to comment on that. Okay. Yeah.
Here it is written in once the transactions are confirmed in the side chain, they're written back to the main chain. So if we can see, if we can imagine each transaction being confirmed and then written. So for example, if spurious transactions they happen on the side chain, each transaction is recorded on the main chain. Then cannot we verify the history and say how it went wrong?
So this is what the side chain is essentially endorsing that transaction, right? And it might not be a valid transaction.
But we are writing the transaction on the
And that kills the point of sidechain to faster transaction.
So
Yeah, so essentially you would like to use, if you're writing every transactions that you're writing on the chain, that is not what you want. Maybe after you finish a lot of these transactions and finally you're writing back something.
but the slowing process was validation, right? If we are
Yeah.
validating,
So you're not validating each and every transaction. So you're validating each and every transaction on the side chain. That could be that can happen quickly.
but we are recording the transaction on the main chain. Or
Not every transaction.
So all the things that happens on side chain will be written on the main chain as well.
No, this is separate.
This is separately running.
Yeah. So so your transaction, if you're saying that I've chosen Polygon sidechain, it will run on Polygon.
Okay, and how it will be connected to main chain? And you are telling that if side chain security is compromised, then the whole main
Yeah.
chain security.
Right. It is a bridge who will help you to connect back.
So bridge will be in the starting only, now ma'am.
There are two-way peg bridge, means like the bridge functionality will give you an entry and exit.
Okay, so when I started my side chain, it depends on me when I want to finish that side chain. It's the ending point.
Yeah, you can use the bridge. The bridge essentially has two parts.
Right.
Once is like you're connecting from here to here, and when you're connecting back,
So it's like entrance system and
exit.
exit system.
Maybe my arrows are making, maybe this arrow is better.
It's okay, my
Yeah.
arrows are okay. Like I'm entering in another chain,
Yeah.
I'm connecting multiple people, and whenever the chain is like forking happens, so I am finishing with the
Nothing forking. There's no concept of forking here. This is all your transactions are happening here. So all your transactions are happening in your Polygon,
right.
right?
The chain doesn't end like, as far as I know, the chain doesn't end by after
No,
the bridge,
that's
yeah.
yeah. When I say chain, okay, maybe this is creating a problem. When I say chain, okay, so there could be more blocks here.
Right. Yeah. Okay.
Right?
It's
So my transaction, so there's one point of entry and one point of exit,
okay.
right? But all the transactions that are happening here, yeah, those are being decided, or those are being validated here.
These
It's
are
not
mine.
being validated here.
Right. So exit point.
Okay, so you want to close that. Say for example, you want to make some transactions, right? So at the end, when you're done all the transactions, so this is a chain. I mean, there could be others who are. So when I say, okay, maybe I'll just draw one picture, which might be a little bit easier to see. So it's something like this. This is your Ethereum, or Ethereum, and this is another network. Yeah. So the bridge is essentially connecting like this. So you would say, for example, so this is bridge 1, B1. So this is bridge service 1. There could be another person who is also using another bridge, right? But whatever is happening, whatever you are doing, you are doing everything on this chain. All your transactions be confirmed here. Okay, and once these transactions are finished, these are coming back, and you are writing the summary on the not summary. I would not say summary, because then you will confuse with the roll up things.
Yeah.
So lastly, if everything is finished, then you are closing it on this Ethereum. So there's a way to connect. Say for example, I have Ethereum. I will convert to Polygon, and then I'm doing everything. Then I might essentially exchange with Ethereum back.
And who will decide when to close? Because
You.
it's chaining.
You.
No, chain is going, ma'am.
No. This chain will still go on. This chain is still going on. Whatever transactions you are doing are getting into blocks over here.
Right, ma'am.
That's what I'm saying. So chain is going. Your chain, I mean, the chain second is going. When I say that you're writing something, it's not on this chain and the chain is closing. It's a transaction. The blocks are here. The side chain blocks are here. Maybe your transaction can get into this block, maybe not this block, maybe these two blocks. Yeah, but the chain is going. That side chain, maybe your transaction might be going in all the blocks here. You might be writing on all the blocks here. That's what I'm saying. And then you're exchanging back with Ethereum.
So sidechain can be only like Ethereum and Ethereum.
Ethereum and Polygon. This is Polygon, say for example.
Sidechain can be anything. Because the sidechains can be anything. It doesn't have to be a layer 2 solution.
No, this is not layer 2. I mean, this is what I was about to say. Sidechain is a way to scale. Typically, when we say layer 2, they inherit the security of layer 1. Okay, this is a point. I'm just trying to
I've
see.
seen bridges
Yeah.
between Solana and Ethereum. Both are layer 1.
Yeah. Bridge can be used for both.
So no.
Bridge is a normal concept. Bridge is anything that connects to blockchains. Bridge is anything that connects to blockchains. It could be Solana, Ethereum. It could be Ethereum, Bitcoin. It could be a sidechain project. There are many small projects also. Like it's not like a big blockchain. So bridges could also connect. I mean, those with those small sidechains.
So when we are saying when we are going to transact Ethereum with Bitcoin, suppose I am paying in Ethereum and you are taking it in Bitcoins.
There also you can.
sidechain.
That's essentially, I would say, there also you need bridge.
Yes, sir.
You need bridge. So that is also possible. So this is your Ethereum. This is your Bitcoin. Bitcoin. Okay. And you need this chain here. This is not chain. What is it? Bridge. Bridge. What bridge does is that it takes money from here, locks it up, and then converts. Yeah. The same thing is happening. Only that all your transactions here are happening. This could be like maybe a one-time process, and this is like all your transactions are happening, and then you are returning back. But the concept of bridge is to connect any chain. Okay, so that is a more generic concept. Bridges can be used for connecting any blockchains.
But I guess bridges can also be centralized and decentralized. Like
There's also all sorts of things. I'm not going into this. Yeah. Because there's a lot also in bridges.
Yeah.
Because bridges are a very vulnerable point in blockchains. There's a lot of money laundering happening in the bridges, because bridges, what they do, as I said, is bridge will lock your money and then make a transfer there. So there's the I can't remember what is it. I can't remember that bridge. They had a lot, a very big fraud. I mean, there are many such bridges actually that have been fraudulent. Okay, but good questions. Question? Any more?
Why sidechain?
Why sidechain? Okay, because all my transactions are happening very fast, and those sidechains are typically smaller things, and the process is quite fast. So that's one. Yeah. So this is a very important thing, and good that you brought it up. I don't know if it's in the slide. It was in one of my earlier slides. I don't think it is. The sidechain is essentially not a strict layer 2 solution, and the only reason I can say is the security of the system relies on the sidechain. But this is a way to scale. Question.
You said that side chains means we need bridges. So you said that, and you also said that the transaction can be done faster with the side chains. So everybody is going to obviously use this, and security is getting less.
Not everybody will do.
So why they won't switch to this one?
Yeah, because sometimes you would need higher security, and you don't want to rely on this third party systems. So it's a choice, but you have that choice.
How would you like classify a chain as if it is a side chain or not? Like if I make a chain, like how would I say if it's a side chain of Ethereum or not? Like, does it only need to have bridge?
If it is a side chain of Ethereum,
Because it doesn't need to be layer 2.
No.
It just needs to be bridges.
Yeah.
But
not
everything with bridges are side chain as well.
Not everything with bridges are
Bridges
okay.
to Ethereum.
Okay, yeah. So the thing is that when all your transactions are happening somewhere else,
Yeah.
right? So side chains typically are smaller projects, which are
Not a concrete definition.
no,
of side chain,
that's
I
not a
guess.
concrete
Yeah,
definition.
exactly.
That's not a concrete definition.
I guess so.
But bridge can be used for connecting
Anything.
anything exactly. Okay. Now, okay. Any more questions? Maybe we can take them later if yeah, any more there, because there will be more here. So yeah, we'll let's look into the blockchain actors now. So we have the clients, miners, and the validators, right? Yeah. So sometimes we would say like the miners, validators. So these are all terminologies, and I'm using them in a kind of a interchangeable way. So these are called miners. These are called operators. Many things, and I'll talk about these in a bit. But at this point, just think about it that the clients or users are creating transactions. The miners are the ones who are creating the blocks, and then the validators are one who are validating the blocks. Now, yesterday in Ethereum, I said these are the validators. So the terminology is a little bit. I'm just using it very loosely, but at this time, this is what I will be using. Okay, so we need quick validation. That's for sure. So if we verify every transaction, then it's going to be slow. So we keep the current state and validate against a set of transactions, and operators and miners need to keep operators or miners would need to keep all the transaction information. So there are a couple of questions that we want to address. First of all, these operators or miners, they are keeping all the transactions. So how do we reduce this amount of storage of these transactions? And how do we ensure that the validation is very quick? Validation of the blocks. So here are some of the scaling questions. So the first question is that when I'm doing all these off-chain transactions, can I delegate this task of bundling the transactions to an operator such that the layer 1 only validates the blocks? So think about it that I'm doing this off-chain transaction with you. If I could use this model that with all the transactions that I have made of the rent transaction throughout the year, I can just make a summary of the transaction and write it back. Can we do it? Can we have a party or a delegated authority or someone who will do all this bundling in a way that is correct? Not a single transaction is dropped or something. Such that the peer nodes only validates the blocks. And question is like, how do I do the computation? Where do I store the data? These are all questions that will come about if I'm doing an off-chain transaction. How much information will the layer 1 protocol need in order to validate a set of transactions? So I paid the rent for 12 weeks. How much information should I give to layer 1 to validate that this is all done correctly? And most importantly, where do I keep my states? How do I maintain? How do I validate? Where do I keep all my transactions so that it's still small at the same level? It has the same level of security. that is provided by my layer 1. Okay, so this is something that we have seen yesterday. So we have seen this world state information, which is a real crucial information. So rest of the talk, I will talk more about the world state, because this is something that we will play with a bit. Okay, so so this is a picture I showed yesterday. And the way the Merkle-Patricia tree works is that all your data is kept on your leaf node. And if you have these addresses, so think of these as address and some values. It's a very simplified form. Each of the accounts have a lot more information. It has account values, nodes, etc. But think about it that these are the keys and values. So think of the key as the account address and the value is the rest of the information. So it's essentially a key value pair. Okay. So a lot of data structures store data as a key value pair. And given the key, you can retrieve a value. Okay. So the key it's also called, a primary key if you are thinking of the database database terminology. So this is a key value pair. So if I give you the data, it should be able to retrieve the value. So the ways the keys are stored is like in the form of a trie. So for example, if you have A7, so your A7 is here, then 1. So this is 1. And then you have the key end. So essentially, if you have to go to this, you will go from here to here and back here. And similarly, if you have A7, so essentially the way you do the trie and then compress it, right? I don't know if you have done tries in your data structure course, but if you're not, just go and revisit. So because this is a common to all, you have this field here, and then you have 1, 7. So there are 2 7s. So you would see that 7 has 2 such things. So it comes like A7 7, and then you have 2 such values, 2 such keys, 1 here and 1 here, and then there are similarly there's 1 more here which is F, and then you have the key. So this is how a Merkle-Patricia tree looks like. All your data, all the data from here is on the leaves, and these are your branch nodes or an extension node. Extension because this is extending. It's like 2 leaves here, but this is a branch node, meaning I'm connecting to a leaf node only. So yeah, this is how it looks like, and all of this is hashed here, and the final hash is kept on chain. So this is what Merkle-Patricia tree looks like. Just like Merkle tree, if I want to prove the existence of this, I will give this node, these 2 nodes, and these 2 nodes and this node, because given this node, I have to prove this. So I will be able to compute this, and with these 2, I will be able to compute this, and then I can match with my root. Yeah, it's just like a Merkle tree. It's just represented. For people who are interested, have a look into data structures, because data structures is extremely crucial if you're really looking deeper into the blockchain space, because these are things that will come up again and again. So I think we talked about this as well. So I'm just skipping this. So this is Merkle tree, and okay. So think about think about the states. So for every state, there's the Merkle-Patricia tree. So here I have made a simplified assumption. I've just considered a Merkle tree, but in general, for every state, there is a Merkle-Patricia tree. Now, when I say that there are transactions T1, TX1, TX2, TXN, now if there is a transaction that affects C and D nodes, C and D accounts, then these accounts are updated, and then this is updated. Okay, is this clear? For example, if you have a transaction that involves nodes E and G, then everything is updated and all the paths are updated and the new state root is computed. Is this part clear? Because this is important for the rest of it. How a state looks like, what happens during a state transition. During a state transition, all the transactions that are affecting the accounts, those are updated and all the paths are updated. Shruti, is it a class here?
Pardon me?
Is it a class here?
I don't know. It might be now. It's 11 o'clock.
Oh.
Are they having class?
And this other guy is also full.
As if here, each leaf node of the multiplication drive is stored in the account information, right?
Is doing that?
The leaf nodes is said we are storing the account.
That's also busy.
Huh?
That's also busy. Just give me 2 minutes.
Okay.
Just give me 2 minutes.
Each leaf node we are storing the account.
Say louder so that
In each leaf node of the tribe, where all the accounts were registered with the blockchain network, right? So, you said we are storing each point with key value pair of each account. So, what does the key value?
key is the account address and value, you can think of the rest of the things.
The private and the public.
Sorry, key. Okay, key. So this key is not a cryptographic key. This is just an index. Yeah.
Yesterday we told that quite a few fields, right? Public.
Yeah, exactly. Okay, this is a good point. Maybe I'll just mention this while they're checking if we have to move from here. So think of, okay, so this is, when I say key and value, key, okay, so this is an index. It's a primary key. If you think of the database literature, it's a primary key. Okay, so it's like key. This is an index, and I retrieve the value from here. In the case of accounts, so your key value pair would be your address, and then rest of it would be account information. Value of that account. Then you would have the nonce and anything else that will be here. Okay.
The account try you talk about
Yeah.
the smart contract which is also stored in the value part.
Yeah. Smart contract. Yeah. The value for some contracts you would have those as value fields as well. Okay, so what we'll do, there's a class next, this class that's going to be conducted in this room, so we'll close it for today. I still have a few things to say, which we'll continue tomorrow. Okay, thank you very much.
Yes.